Look at this question. For the circuit shown below, assume that the Zener diode is ideal with a breakdown voltage of 6 volts. The waveform across R is. See, if you compare the previous circuit, here the positions of Zener diode and resistor are changing, nothing else. The direction of Zener diode is also not changing. See, in this circuit, you can even write V input is equal to, if you take the loop equation, what I meant to say is, this is our input and it is voltage across the diode from cathode to anode, and voltage across the resistor is VR. So VD plus VR we can write. Then look at the previous problem. Here also what we can write, again V input, the same circuit only, and it is VR and it is VD from cathode to anode. So if you take this loop equation, we can take V input is equal to VR plus VD, nothing else. Okay, V in input is not changing and resistor value is not changing. Zener diode breakdown voltage is also not changing. So in this problem, we have observed, we measured voltage across the diode. Now in the same problem, what is voltage across the resistor they are asking? It's very simple. What you can write, you know VD, then VR is equal to V in minus VD. It is as simple as that. Okay, that's one way of analyzing it as we know this problem. Okay, so based on that we can see the transfer characteristics, etc., etc. Right, anyway, let us go with our regular analysis. In the exam you see a circuit of this kind, then how will you do this problem? Okay, that's what we need to see. Okay, so instead of all these things, I'm just going this with a regular approach. What is our regular approach? Vary the input from minimum to maximum. Then take the possible cases. Okay, input is at its negative peak of minus 12 volts. Then what happens to the generator? Minus 12 means it is like connecting a negative source to the circuit. Then cathode is connected to negative terminal and anode is going towards the positive terminal. Diode is forward biased and simply acts as short circuit. Okay, so case 1, diode is forward biased, or diode is on or forward biased. If the diode is forward biased, then it acts as short circuit. VR or V output. Let me take V output also, doesn't matter. Then what is V output? Output is equal to input. We can see. And how long this is possible? As long as the input is negative, means complete negative half cycle. You are starting with minus 12, and if as long as input is negative, diode is forward biased. That's it. Or instead of that, I can say input, instead of saying input is negative, right? What I can say is less than breakpoint, right? Above circuit is valid if V input is less than breakpoint 1. We can take. Keep it aside. Next, input is positive but less than the breakdown voltage of the Zener diode. Then what happens? Positive but less than breakdown voltage of the Zener diode. Then diode is open circuit. Diode does not conduct. Okay. So second case. Case 2. Diode is reverse biased. Then it simply acts as open circuit. What is the output? 0. How long this is valid? This is valid as long as input is positive, at the same time less than the breakdown voltage of the Zener diode. Means 2 breakpoints we can see. Above circuit is valid if breakpoint 1 less than V input less than breakpoint 2. That's it. Breakpoint 1 means right, beginning point of positive, that may be 0 volts, and breakpoint 2, that is breakdown voltage of the Zener diode, that is 6 volts. Okay, next case 3. See this basic circuit. Input is greater than 6 volts or the breakdown voltage of the Zener diode. Then what happens? The Zener diode maintains a constant voltage of 6 volts across it, and the remaining voltage input minus 6 will be appearing across the resistor. Okay, so diode is under Zener breakdown. Then it maintains 6 volts from cathode to anode. Then what is V output in this circuit? It is V in minus 6. We can write V in is equal to 6 plus V output, or V output is V in minus 6. And above circuit is valid if V input is greater than breakpoint 2, means greater than breakdown voltage of the Zener diode. Now at breakpoint 1, what we can take? Output is equal to input, and also output is equal to 0, implies breakpoint 1 is 0 volts. Fine. At breakpoint 2, output is equal to 0, also output is equal to input minus 6, implies breakpoint 2 is equal to, or what is V input? 6 volts. Okay, that is 6 volts. Now if you observe the transfer characteristics, one graph is like output is equal to input. It is a straight line passing through origin. First one, input less than breakpoint 1. Next, second one, output is equal to 0, that is y is equal to 0, means x-axis. Here we can see one breakpoint. And third one, output is equal to input minus 6, means it appears like a straight line parallel to the previous one. Why I am saying so? Here output is equal to input, its slope is 1. Here output is equal to V input minus 6 I am writing. It is like y is equal to x minus 6. Okay, it is meets the y axis at minus 6 volts. Okay, intercept on y axis is minus 6. Okay, let us combine all these three. So this is our breakpoint 1, it is 0, and this is the second breakpoint, breakpoint 2, it is 6 volts. So input less than 6 volts, output is equal to input. Input is in between 0 and 6, output is equal to 0. Input greater than 6, output is equal to input minus 6. These are all for our better understanding only, nothing else. Okay, this is how we can do it. Now you can even compare with the very beginning I told, like VR is equal to V in minus VD. Okay, so if you take the previous problem, here first V output is equal to 0. First case means VD is 0. Then what is VR? V in minus VD, that is V in minus 0, that is V input only. That is for input less than breakpoint 1. Breakpoint 1 and breakpoint 2, they do not change. So input less than breakpoint 1, VR is equal to V input and VD is 0. Absolutely we are getting. Second case. And The input is in between breakpoint 1 and breakpoint 2. What you can observe means 0 and 6 volts. Here VD is equal to V input, then VR will be 0. Absolutely, we can see that VR is equal to 0. Okay, in between breakpoint 1 and breakpoint. Third one, okay, input greater than breakpoint 2, output is equal to 6 volts. Means VD is equal to 6, VR is equal to V in minus VD, that is V in minus 6. This is what we have got. Everything is fine. Anyway, these are all for our better understanding purpose only, right? We can write the waveforms, it's not a big deal. Now, if you look at the waveform, finally, output is equal to input when input is a negative cycle. Okay, as long as input is negative, output is equal to input. Negative cycles means I can just write them as they are. Next, 0 to 6 volts, output is 0. And input is above 6 volts, above breakpoint 2, output is equal to input minus 6. Means, suppose input reaches 12 volts, that time it is 12 minus 6, 6. So, output reaches a maximum of 6 volts. Like this. Again, 0 to 6, output is 0. And above 6 volts, it is input minus 6. When input is a negative going cycle, that time output is equal to input. So this is how we can observe the output waveform. Now look at the options. Option B is correct. Okay. And positive cycles output can reach a maximum of 6 volts. Negative cycles output can reach a minimum of minus 12 volts. That's it. It's a very simple one. Next, see this question. A Clipper circuit is shown below. Assuming forward voltage drops of the diodes to be 0.7 volts, the input-output transfer characteristics of the circuit is. Okay, transfer characteristic of the circuit is. Okay, how do we do this? Of course, a similar one I have drawn already, right? If you see this circuit, yes, diode is upwards D2 and 6 volts. Instead of 6 volts, what we have there? 5 volts. And here the diode is ideal. We got the transfer characteristics like this, right? Actually, we have only one GNR diode. This circuit gives the transfer characteristics same as that of a circuit of this one. Okay? Or this circuit will give the same waveforms. Okay, so similar one, but instead of 6, we have 5. Means if the diode is ideal, the same transfer characteristics, similar waveform, instead of 6, I can write 5. But they have given diode forward voltage drop as 0.7 volts. Then how do we do this problem? If the diodes are ideal, we know the answer. Okay, right. And let us take the first case. Let us start with input negative peak. Suppose input is at its negative peak. It is not mentioned. Okay, negative peak. Let us assume it has a negative peak in such a way that the diode is under forward bias condition. Okay, for that D1, I can say D1. So it is negative means the anode of diode D1 is going to positive terminal, cathode is going to negative terminal, diode is forward biased. Ideally short circuit, practically it maintains 0.7 volts from anode to cathode. What about D2? D2, its anode is connected to negative terminal, cathode is connected to positive terminal. It is reverse biased, open circuit. So the very first case I can take is D1 is on and D2 is off. This is possible when input is at its negative peak. So the equivalent circuit. Five volts are input. So what is V output? Minus 0.7 volts. Okay. And how long this is true? Actually, this is true as long as input is negative. Or instead of negative, I can say breakpoint 1. Above circuit is valid if V input is less than breakpoint 1. Keep it as well. Next, input is positive. Then D1 will be immediately off. Positive at the same time, it may be 1 volt, 2 volt, 3 volt like that. And it is less than 5 volts. For D2 to conduct, input should be more than 5 volt. Okay. So I am taking a case where input is positive but less than 5. Instead of saying 5, I am saying breakpoint 2. Then what happens? Anyway, as input is positive, D1 is off, D2 is also off. Both D1 and D2 are off. Case 2. Both D1 and D2 are off. So from this circuit, what is the relation between output and input? Output is equal to. How long this is valid? Input should be positive and less than 5. Positive in the sense greater than 0 and less than 5. Instead of writing 0 and 5, I am writing breakpoint 1 and breakpoint 2. Above circuit is valid if breakpoint 1 less than V input less than breakpoint 2. That's it. And third case, case 3. Input is greater than 5 volts or greater than breakpoint. Then what happens? D2 starts conducting. Anyway, D1 is off, D2 is on. Ideally means short circuit. Practically, it maintains 0.7 volts across it. Okay. So D1 off, D2 on. So what do we get? V output, V input, and it is 5.7. When is this possible? It is possible for input greater than breakpoint 2. So now let us find those two breakpoints. At breakpoint 1, output is equal to minus 0.7 volts and also equal to input. Implies breakpoint 1 is minus 0.7 volts. at breakpoint 2 output is equal to input and also equal to 5.7 implies breakpoint 2 is equal to 5.7. Then if you take the transfer characteristics, one equation is like output is equal to minus 0.7 volt. One equation is like output is equal to input, that is case 2. Next, case 3, output is equal to 5.7. Then we can see two breakpoints. This is one breakpoint and this is another breakpoint. Its value is minus 0.7 and it is 5.7. So input less than breakpoint 1, output is minus 0.7, and input greater than breakpoint 1 less than breakpoint 2, output is equal to input. Input greater than breakpoint 2, output is equal to 5. That's it. If the diodes are ideal, then what we might have got? Definitely the transfer characteristic might be like this. If the diodes are ideal, the breakpoints are 0 volts and 5 volts. As the diodes are practical, then voltage drops of forward voltage drops of diodes are taken into consideration. That's it. Okay, we have already seen this problem in terms of a simple GNR diode with a breakdown voltage of 6 volts. Right. This is the idea. Okay, and what did they ask in this problem? They asked us to draw the transfer characteristic. What do we get? Minus 0.7, right? And here it is 0 and it is 5.7. That's it. Option C is correct. That's it. Next. See this question. It is similar to the previous one only. Only thing is instead of D1, they kept GNR diode. That's it. Okay, read the question. See the question. The Clipper circuit is shown below. Assuming forward voltage drops of the diodes to be 0.7 volts and the GNR breakdown voltage of D1B 10 volts, then input output transfer characteristic of the circuit is yes. D1 is a GNR diode with a breakdown voltage of 10 volts. That's it. Okay. Then how do we do this problem? As usual, comes similar to the previous one only. So first case 1, input is at its negative peak. Then what happens to D1? It is behaving like ordinary diode because okay, negative peak means its cathode is going towards negative terminal, anode goes towards positive terminal, it is forward biased. And it behaves like ordinary diode. And when it is forward biased, it maintains a voltage of 0.7 volts. What about D2? D2, its anode is going to negative terminal, cathode goes towards positive terminal anyway. So D2 is off. D1 is forward biased and D2 is reverse biased. Case 1. D1 is forward biased and D2 is reverse biased. Means across D1, I can write 0.7 volts from anode to cathode. D2 is open circuit. V output, input. Okay. Then what is V output? Minus 0.7 volts. And how long this is valid? This is valid as long as input is negative or less than 0 ideally. Or I can say less than breakpoint 1. V input is less than breakpoint 1. Next, input is positive and less than 5 volts. Right? Instead of that, I can say greater than breakpoint 1, less than breakpoint. What happens? Positive means it is reverse biased. And less than 5 means this is also reverse biased. Both D1 and D2 are off. Case 2. Both D1 and D2 are off. What is V output? Input. And above circuit is valid if breakpoint 1 less than V input less than breakpoint 2. Similar to the previous one. Next. Case 3. Input is greater than 5 volts or greater than breakpoint. Then what happens? D1 is anyway reverse bias. D2 is forward bias. D2 is forward bias means, right, it maintains the voltage of 0.7 volts across it. Okay. It looks like D1 has a breakdown voltage of 10 volts. Okay, it looks like. So what I am doing is input is greater than breakpoint 2 and less than breakpoint 3. Okay. Anyway, D1 is reverse biased and D2 is forward biased. The equivalent circuit. Then output is equal to 5.7 volts. It looks like there is a scope for D1 to undergo breakdown. As it is in our diode, suppose input is greater than 10 volts, which is the breakdown voltage of D1, then there is a scope for this to undergo breakdown. It looks like. Don't worry, I will conclude everything. Right? So, I'm writing it. Above circuit is valid if breakpoint 2 less than V input less than breakpoint 3. Okay. Let it be. Further, I am increasing the input above 10 volts. Okay, here in this, my input is 6 volts. What is the output? 5.7 volts. 7 volts, 5.7. 8 volts, 5.7. Is there any scope for the voltage across these two terminals to rise above 5.7? No. 9 volts? No. 10 volts? No. 11 volts? No. In this, if you see in this direction, right, it looks like 11 volts. Between these two, it is going above 11 volts. But if you see in this direction, what is the maximum voltage possible across these two terminals, friends? 5.7 only. Then, is there any scope for D1 to undergo breakdown? Impossible. It cannot undergo breakdown at all. See, actually what is happening here is when 6 volts, Here 5.7 voltage across 1K will be 6 minus 5.7, 1.3. When input is 7 volts, okay, this part 7 volts, then the voltage between these two terminals is 5.7 only, but this becomes 1.3. The current in the circuit will increase. What is the current I can take? 6 minus 5.7 by 1K, that is 0.3 milliampere when input is 6 volts. When input is 7 volts, then 7 minus 5.7, that is 1.3. 1.3 volts by 1K, 1.3 milliamperes is the current flowing. And again 8 volts, 2.3. When 9 volts, then it is 3.3. 10 volts, 4.3. 11 volts, 5.3. Voltage across the resistor keeps on increasing, but voltage across the Zener diode remains constant at 5.3. There is no scope for voltage across the Zener diode to rise above 5.7, even though the input is 11 volts, 12 volts, 13 volts, like that. See the interesting point here. The moment people see that, observe the Zener diode, yes, input is going about, and right, its breakdown voltage 11 volts, like that. Then Zener diode is undergoing breakdown, and they say it is voltage across the Zener diode is 10. Then is it possible to see 10 volts parallel with 5.7? Is it possible to see 5 volts across the forward bias diode D2? Because the voltage across these two terminals is 10, which should be, means out of which out of 10, 5 is already appearing across the diode. And is it possible to see 5 volts across the diode D2, which is under forward bias? Impossible. DT is forward biased, voltage across it is at a max 0.7 volts. So the total voltage across the Zener diode is 5.7. It can't go beyond 5.7, even though the input goes above the breakdown voltage of the Zener diode. Then what happens to the remaining drop? That can be seen across the 1 kilo ohm resistor. Okay, 1 kilo ohm resistor will take care of, that's it. So there is no scope for the Zener diode D1 to undergo breakdown. It cannot undergo breakdown. This is a very interesting point in this one. Okay, people see this from this direction. Right? People just look from this direction. As the input is going above its breakdown voltage, it will. But if you see in this direction, the voltage across these two terminals cannot go beyond 0.7. Sorry, 5.7. Why? Right, as the voltage between these two terminals is 5.7 and input is 11, 12, like that, then what happens to the remaining drop that can be seen across 1 kilo ohm resistor? Okay, D1 is anyway open circuit, and in this circuit the current keeps on increasing with increase of input. Accordingly, voltage across 1 kilo ohm will increase, and overall output can take a maximum of 5.7 volts. This is the interesting point, and there is no point of breakpoint 3, even though I wrote it here. Okay, so when input is exceeding breakpoint 2, then automatically the output cannot go, output reaches its maximum value of 0.7 volts, and that is not at all sufficient to cause D1 to undergo Zener breakdown. Okay, it is written just for our understanding purpose, right? It's not like breakpoint 3 is possible. Breakpoint 3 is not possible. I'm just erasing that. So now let us take the breakpoints. At breakpoint 1, output is equal to minus 0.7 volts, also equal to input, implies breakpoint 1 is equal to minus 0.7 volts. At breakpoint 2, output is equal to input, and it is also equal to 5.7 volt, implies breakpoint 2 is equal to 5.7 volt. It is same as that of the previous one only, right? So ultimately what we can see here, the transfer characteristics, if you observe, so Same as that of this problem. Is it not so? Okay. So if you see the transfer characteristics, once output reaches its maximum value, further, even though you increase the input, output does not increase. That's it. Okay, so even though we have a Zener diode instead of D1 here, a Zener diode is kept, it does not influence the transfer characteristics. That's it. Just to make you aware of this, right? I did this problem. There is one thing possible. Let us take the same problem, and if D1 has a breakdown voltage of 4 volts, then what happens? Or 5 volts. Okay. What happens? See, or 4 volts I'm taking. Just suppose the breakdown voltage of diode D1 is 4 volts. Then repeat the above problem. What is possible? As usual, right, input is negative, right? Case 1, I can take D1 is on and D2 is reverse bias or off. Then it maintains 0.7 volts from anode to cathode and input. Output is equal to minus 0.7 volts. This is valid as long as input is less than breakpoint 1 or input is negative. Okay. Input is less than breakpoint 1. Ideally 0. Practically it is minus 0.7 volts. Okay. Next, case 2. Input is positive and less than breakpoint 2. What might be the breakpoint 2? Okay. Two things. Here, generally what we think is 5. But if you look at the breakdown voltage of D1, it is 4 volts. It is a smaller value. We have to look at the smaller value first. Which comes first after 0, 1, 2, 3, 4 comes first. 5 comes later. So breakpoint 2 might be 4. Okay. So if input is positive and less than breakpoint 2, then D1 is off and D2 is also off. Both D1 and D2 are off. Then output is equal to input. Okay, how long this is possible? breakpoint 1 less than V input less than breakpoint 2. Okay. Next means breakpoint 2 might be 4, something like that, not 5. If input is more than 4 and less than 5, what happens? D1 undergoes breakdown, but still D2 is reverse biased. Okay. Case 3. D1 is under GNR breakdown and D2 is still reverse biased. Okay. Then what is the equivalent circuit? Across D1, I can write it's VZ, that is 4 volts from cathode to anode, and D2 is still open circuit. So what is the output, friends? 4 volts. Okay, it looks like this circuit is valid for input greater than breakpoint 2 and less than breakpoint 3. Just I'm writing it. We'll see what are all the things possible. Above circuit is valid if breakpoint 2 less than V input less than breakpoint 3. Okay, fine. Further, you are increasing the input voltage, maybe more than 5 or more than 6. What happens? Is there any possibility for voltage across these two terminals to be going above 4 volts? No. Input may be 5 volt, 6 volts, 7 volts, 8 volts, 9, but voltage across these two terminals cannot go beyond 4 volts. Once it is undergoing breakdown, over, there is no scope for D2 to forward bias. Input may go above 5, but voltage across the GNR diode is not able to go above 4 volts, and hence diode never conducts. Diode D2 never conducts. D2 acts as open circuit and output is equal to 4 volts. So I need not worry about writing this breakpoint 3. Input greater than breakpoint 2. That's it. Your input may keep on rising, doesn't matter. The voltage across resistor will increase. That's it. Here we have 1 kilo ohm. No? So input 6 volts means the remaining 2 volts will be across this 1k. 7 volts, then voltage across 1k will be 3 volts. Like that. Then if you take its transfer characteristics, first equation is V input is minus 0.7. Next, output is equal to input. Third equation, third case, output is equal to 4 volts. So the first breakpoint minus 0.7 volts. Second breakpoint is 4 volts. It is not 5.7. There is no point of further any breakpoint. That's it. This is how we can observe the transfer characteristics for this case. Okay. In the previous problem, the GNR diode has a breakdown voltage of 10, which is not possible to reach. But here, the breakdown voltage is less, and hence there is no possibility for D2 to conduct. D2 never conducts. Okay. This is how we can do this problem. Now we can easily understand. Okay. And one more thing, friends. Ultimately, what we can do is, instead of this 5 volts, I can place even a GNR diode. What I mean to say is, here itself I would like to discuss all these points. Let us take this problem. Here I am placing one more GNR diode. D1, D2, D3, some are 1 kilo input, output. Okay, and V gamma, the diode forward voltage is 0.7 volts, and VZ3 breakdown voltage of GNR diode is 5 volts. Then draw the transfer characteristics. Okay, then how do we do this? As usual, input is at its negative peak, D1 is forward biased, and what about D2? D3 is also ready to forward bias, but D2 is in series with it. There is no scope for D2 to conduct, and hence D3 also does not conduct. Okay, so case 1, coming to its solution. Case 1, D1 is forward biased, D2 and D3 are reverse biased. D1 is on, D2 and D3 are off. You see, D1, D3 are in the same direction, but unfortunately, what is happening? D2 is in series with D3. DT is for D2 to conduct, input should be negative. Input should be positive. Sorry, input should be positive. But the present input here is negative, for which D2 input is at its negative peak. D1 is forward biased. D2 is reverse biased. As DT is reverse biased, even though D3 is ready to conduct, it can't conduct. So the equivalent circuit. Output is equal to minus 0.7. How long this is valid? It is valid for input negative. Instead of that, I can say breakpoint. Okay, done. Next, case 2. If V input is greater than breakpoint 1 and means positive and less than breakdown voltage of D3, because if input is positive, then D1 is anyway off. D2 is ready to conduct, but what about D3? D3 is reverse biased, no? D1 is reverse biased, and D3 also will be reverse biased. It is receiving a positive voltage from cathode to anode. It cannot conduct. Once D3 is open circuit, there is no scope for D2 to conduct. D2 also becomes open. D2 is trying to conduct, but as D3 is not conducting, D2 also has to keep quiet. That's it. So all the 3 diodes D1, D2 and D3 are off. No diode conducts. If all are off, the equivalent circuit is something like this. So what about output? It is equal to input. That's it. Next, how long this is valid? This is valid if the input is in greater than breakpoint 1, less than breakpoint 2. Maybe the breakdown voltage of generator 5 volts like that. So It looks like 0 and 5. We'll see. Further, we are increasing the input above breakdown voltage of D3, means above 5 volts like that. Then D3 is ready to undergo GNR breakdown and D2 is forward biased. So input is positive, D2 is ready to forward biased. What about D1? D1 is anyway reverse biased. D1 is reverse biased, D2 is forward biased, and D3 undergoes GNR breakdown. That's for input greater than breakpoint 2. Case 3. Okay, here I will write it. D1 is off, D2 is forward biased or on, D3 is under GNR breakdown. So what is the equivalent circuit? It is 0.7 from anode to cathode, and it is 5 volts from cathode to anode. Ultimately, what is the output? V output is equal to 5.7 volts. And how long this is valid? This is valid for input greater than breakpoint. Input is greater than 5.7, then it is same only. Okay, so maybe 6 volts, 7 volts, 8 volts, 9 volt, and more like that. So if you observe these three cases are the same as that of the previous ones we have studied, not this circuit. Okay, even though you have GNR diode, right, its characteristics are same as that of this one. Okay, this circuit, instead of D1 I kept GNR diode whose breakdown voltage is 10. Next, the third one I kept here, instead of 5 volts I kept a GNR diode whose breakdown voltage is 5 volts. These three problems will give the transfer characteristics same as that of this. Okay, this circuit, even though D1 is a GNR diode, as its breakdown voltage is more than 5.7, the third case is simply output is equal to 5.7. Now you look at this one. In this, so what we can observe is instead of 5 volts battery, I can place a GNR diode whose breakdown voltage of 5 volts. That will also give us the transfer characteristics same as that of the previous. Okay, so this circuit and one more circuit what I wrote here, there may be a GNR diode, but its VZ is 10 volts, so it does not play any role. And third one, it may be ordinary diode or GNR diode whose right. If it is GNR diode, it may have a breakdown of 10. Doesn't matter. Next, D2 remains as it is. Instead of 5 volts battery, I am placing here a GNR diode whose breakdown voltage is 5 volts. All the three are giving us the same result. Okay. Next, see this problem. In the following voltage limiter circuit, at an input voltage Vi is equal to 10 sin 100 pi t is applied, should write. Assume that the diode drop is 0.7 volts when it is forward biased. The GNR breakdown voltage is 6.8. The maximum and minimum value of output voltage respectively are. It's very, very simple question. Is it not same as that of the previous one we did? Just instead of 6.8 volts, I took 5.5 volts. Then we have seen the results. Okay. Now it is 6.8 volts. So it doesn't matter. So input minimum means when input is minimum, that time that is a negative peak, then D1 is open circuit, D2 is ready to conduct, it cannot conduct because D1 is in series with this D3, let me write. D1, D3 are off, D2 is on. Output is minus 0.7 volts. Okay, so we can blindly take this as our result because output minimum is minus 0.7 from this, and we can see that only in option D. Anyway, it doesn't matter, we will see. So if we input is minimum, that is negative peak, then what happens? D1 and D3 are off and D2 is on. So the equivalent circuit, if you see, output is minus 0.7, that is V output minimum. Next, when input is maximum, here it is given 10 sine omega t. Okay, minimum in the sense minus 10 volts. When input is plus 10, then what happens? Positive voltage D2 is anyway reverse biased. D1, D3. If you see, D1 is ready to conduct and D3 is ready to undergo breakdown. So, if V input is equal to maximum, that is equal to plus 10 volts, then what happens? Here D1 is on or forward biased, D2 is reverse biased, and D3 undergoes breakdown. The equivalent circuit is so we can see 0.7 volts here and 6.8 volts here. So total is 7.5 volt as we are getting. Option D is correct. Okay. It's a very simple question. Multiple diodes instead of reference voltages, etc. Now look at this question. The wave shape V output of the and the transfer characteristics of the circuit shown in figure will be. Okay. What do we get? Two Zener diodes. Instead of one ordinary diode and one Zener diode, they are showing two Zener diodes. Doesn't matter. Case 1. Input is at its negative peak, 10 sine 314t. See, means input is minus 10 volts. Okay, they have not mentioned anything about the diode forward voltage and all, just they mentioned breakdown voltage. Okay, so input is minus 10, then what happens? Minus plus D1, let me take this is D1 and D2. D1 is ready to undergo breakdown. Is it not so? Because its anode is connected to negative terminal, cathode is going to positive terminal. It is reverse biased and it is as it is in our diode, there is a scope for D1 to undergo breakdown. What about D2? D2, its cathode is going to negative terminal and anode is going to positive terminal. D2 is forward biased and D1 is undergoing Zener breakdown. Very simple for negative peak. So D1 is under Zener breakdown and D2 is forward biased. So what is the equivalent circuit? And what about its breakdown voltage? It maintains VZ from cathode to anode, 4.1. So output is equal to minus 4.1. Right. Input is negative peak 2, that is minus 10, minus 9, minus 8, minus 7, minus, right, minus 6, minus 5, minus 4, like that. It decreases. When it falls below minus 4 or minus 4.1 volt, what happens? D1 comes out of breakdown, GNR breakdown. It's not uh, large enough as far as the magnitude is concerned. Not large enough to see that D1 is under breakdown. So once D1 comes out of breakdown, it acts as open circuit. Once it is open circuit, there is no scope for D2 to conduct, even though it looks like it is forward biased. Okay, so okay, here let me write the breakpoint now. Above circuit is valid. Sorry. If V input is less than breakpoint 1. That means like the breakdown voltage of the diode D1. That's what I mean to say. As long as it is less than that, means maybe minus 5, minus 6, minus 7, minus 8, minus 10. Like that, doesn't matter. This is valid. If input falls, rises above breakpoint 1, because you are always changing the input from negative peak to positive peak. Okay, input is going above minus 4.1 volt, means maybe minus 4, minus 3.9, minus 3.8, minus 3.5, minus 3, minus 2, like that. Then D1 is coming out of breakdown. As D1 is coming out of breakdown, it acts as open circuit and there is no scope for D2 to be forward biased. Okay, case 2. D1 and D2 are off. Here output is equal to input. Okay, D1 is coming out of breakdown and D2 is also not possible to be in forward biased. Okay, and how long this is valid? This is valid as long as input is negative, we feel like. Input is negative in the sense, right, it may be minus 1 volt up to that or 0 volts. Even for 0 volts, what happens? No diode is conducting. Okay, either D1 or D2, both are under reverse bias. Okay, next input is positive, 1 volt. Input is 1 volt, then what is possible here? D1 is ready to forward bias, but what about D2? It is reverse bias, no? Its cathode is connected to positive terminal and anode is connected to it. Means both are off. Means the same case continues. 2 volts, same case continues. 3 volts, same case continues. Up to what value? Both are off. So case 2 continues even though the input is positive. Okay. So minus 10 to minus 4.1 case 1 and the equivalent circuit, and minus 4.1 to 0 case 2. Input is positive. Even though input is positive, D1 is ready to conduct. As D2 is under reverse bias condition, D1 cannot conduct. Okay, positive 1 volt, positive 2 volts, the same story. Positive 3 volts, same story. Positive 4 volts, the same story. Up to what value? 4.1. If the input is plus 4.5 volt, for example, then D2 is ready to undergo GNR breakdown. Is it not so? And D1 is forward biased. Okay, that's what we can observe. So even though input is positive, we need not take like breakpoint 2 as some 0 or like that. No, till what time we need to wait? Till the input reaches plus 4.1 volt. That will be our breakpoint 2. Okay, so above circuit is valid if breakpoint 1 less than V input less than breakpoint 2. Okay, breakpoint 1, it looks like minus 4.1. Breakpoint 2, it's not 0 or it's not 1, 2, 3. It is 4.1. Okay, we'll calculate it anyway. Please do observe this point. It's not like once input becomes positive, immediately D1 is on. No, because D1 is in series with D2. D1 is forward biased, D2 is reverse biased. Next, input is above breakpoint 2, means above 4.1. Then what happens? Maybe some 5 volts like this. Then D2 undergoes breakdown and it maintains 4.1 from cathode to anode. Along with that, D1 is forward biased, it acts as short circuit. So that the overall output is 4.1. That is our case 3. D1 is on and D2 is under Zener breakdown. Okay, so what do we get? D1 acts as short circuit and D2 it maintains a voltage Vz of 4.1 volt from cathode to anode. What is output? 4.1. When is this circuit possible? This is above breakpoint 2. That's it. Then let us find those breakpoints. At breakpoint 1, output is equal to minus 4.1 and also equal to input. Implies breakpoint 1 is minus 4.1. At breakpoint 2, output is equal to input and also equal to 4.1 volt. Implies breakpoint 2 is plus 4.1 volt. Finally, if I draw the transfer characteristics here, one equation is V output is equal to minus 4.1 volt and second one is output is equal to input. Third one, output is equal to plus 4.1 volt. Means we can see the two breakpoints like this. Breakpoint 1 is equal to minus 4.1 volt. Input less than breakpoint 1. Output is equal to minus 4.1. And in between breakpoint 1 and breakpoint 2, output is equal to input. Input greater than breakpoint 2, output is equal to 4.1. That's it. With the two Zener diodes, we can see this result, which means this is equivalent to a circuit of this kind. This is two diode clipper we have seen. Okay, D1, D2. Let us take ideal diodes. And this is 4.1 volt and it is also 4.1. If you draw the transfer characteristics for this particular problem, what you can see? Will you not get? Okay, the transfer characteristics same as that of this are. Instead of using two ordinary diodes with two batteries, I can simply go with two Zener diodes. It is as simple as that. This is the final conclusion we can observe. Okay, simply two diodes, no more further extra batteries and all. Ideal diodes. Of course, here D1, D2 are ideal diodes. Okay, that's it. Next. Okay, see this problem. Same previous one only, right? As I told, with single GNR diode I did, now it is with two GNR diodes. See, the resistor and two GNR diodes are kept like this in the previous one. Here V input is equal to VR plus VD. Let me take. Now here V input is equal to, this is VD and it is VR. Both are same. Now we know VD, how it is. Then what is VR? V in minus VD. Here also, what is VD? Right, VD we have seen. But anyway, VR is equal to V in minus VD. VD is already, no. VR we need to drop. So as simple as that. Okay, let us take this one. Input is less than, or input is at its negative peak. Then what happens? D1 is under breakdown and D2 is forward biased. Okay, so case 1. D1 is under GNR breakdown and D2 is simply forward biased. A very similar problem we have seen with single diode, no? So here what do you get? 4.1 volt from cathode to anode output. So what is V output? V in minus VD, minus of minus plus 4.1 it will be. Okay. So VR or V output is equal to V in minus of minus 4.1. V input plus 4.1. Or we have seen with this particular case 1, D1 is under breakdown, DT is forward biased means, right? VD is equal to minus 4.1. Then what is VR? V in minus VD, V in minus of minus 4.1. So V in plus 4.1. It's as simple as it. Above circuit is valid if V input is less than minus 4.1, that is breakpoint. Next, input is greater than breakpoint 1 and less than breakpoint 2. What might be breakpoint 2? Plus 4.1. I'm directly doing this problem, friends, because we did a lot of exercise, right? So many problems. So here, even though it is showing 27, in between, some 3 additional problems I did, I think so, 2 or 3. Okay, so almost 30 problems. I need not again write each and every step clearly, not required. So case 2, I can write input is greater than minus 4.1 and less than 4.1. Then both the diodes are off. Okay, case 2. Both D1 and D2 are off. Simply output is 0. This is valid if breakpoint 1 less than V input less than breakpoint 2. With a single GNR diode, we did the same story with two GNR diodes, nothing else. Next, case 3. Input is greater than plus 4.1 volt. Then D1 is forward bias, D2 is under breakdown. D1 acts as short circuit, D2 holds a constant voltage of 4.1. Then output is 10 sin omega t minus 4, or input minus 4.1. D1 is forward biased and D2 is under Zener breakdown. output is equal to input minus 4.1. That's it. Even here you can see those two breakpoints. Okay, at breakpoint 1, output is equal to V in minus breakpoint 1, V input plus. Also, it is equal to 0. Implies V input is minus 4.1, which is our breakpoint 1. Next, at breakpoint 2, output is equal to 0. Also, it is equal to input minus 4.1. Implies input is plus 4.1 volt, which is our breakpoint 2. Absolutely. Okay, of course, this circuit is valid if input is greater than breakpoint 2. Now, let us draw its transfer characteristics. One equation, output is equal to input plus 4.1. Input plus 4.1. Second one, output is equal to 0. It is like y is equal to x plus 4.1. Intercept on y-axis is positive. Okay. And second one is output is equal to 0. Means it is x-axis. Third one is like output is equal to input minus 4.1. Its intercept on y-axis is negative. So the first breakpoint is here. Up to this, I can take the first equation. Next, minus 4.1 to plus 4.1, output is 0. That's breakpoint 2 is plus 4.1. Next, I should take this equation. Output is equal to input minus 4.1. This is how we can see the transfer characteristics of this particular case. Okay. So with a single GNR diode, we did this problem, similar problem. Okay. Now instead of one GNR diode, two GNR diodes. Okay. What about the output waveform? We have two breakpoints. Okay. If input is between breakpoint 1 and breakpoint 2, what is output, friends? 0. No diode conducts and hence output is 0. If input is less than breakpoint 1, output is V input plus 4.1. So less than minus 4.1, it is anyway. What we can take here is from 4.5 to minus 4.5. Okay, output is simply 0. Between breakpoint 1 and breakpoint 2, output is 0. Okay, but in between breakpoint 1 and breakpoint above breakpoint 2, it is V input minus 4.1. Okay. So input has a peak amplitude of how much? 10. So 10 minus 4.1 peak amplitude. So it is 5.9. It can reach a maximum of 5.9 volt. And again, during negative cycles, what we can see is it can reach up to minus 5.9 volt. When input is at its peak and negative peak, that time minus 10 plus 4.1. It's minus 5. Okay, that's it. This is how we can see the waveforms as far as this circuit is concerned. So it is 5.9 minus 5.9. We can take it. So option A is correct. Option B you can see in the as the result of the previous problem, not this problem. Right, and this problem I did bit faster because we have been doing so many problems, right? We have done a lot of good problems. It is just a very simple one, right? Once you understand this 26th problem, problem number 26, right? I just instead of taking voltage across this two Zener diodes, I am asking voltage across the 10 kilo ohm resistor. That's it. Now see this 28th question. The same problem, right? Not last but one problem, right? See, two Zener diodes are given 10 sin omega t and their breakdown voltages. Oh, anyway, let me read the question into it. Without 1K, what is the result? We are well aware. Some 1 kilo ohm resistor and here also 1K is connected. Then what happens? The breakpoints will change. Okay, it was a question asked in previous gate papers. Of course, in 80s like that. It was a descriptive question. Okay, nothing to worry. So the cut-in voltage of both the diodes shown in figure is 0.7 volts, while the breakdown voltage of Zener is 3.3. Okay, and the reverse breakdown is 50 volts. Avalanche breakdown voltage is 50, Zener breakdown is 3.3 volts. That's what they mean. The other parameters can be assumed to be same as those of ideal diode. Okay, fine. The values of the peak output voltage in both the cycles are peak output voltage. Okay, right. So during positive cycle, suppose it is 10 volts, then what happens? This is under Zener breakdown and it is simply forward biased. Forward biased means short circuit. As it is undergoing breakdown, it maintains 3.3 volts from cathode to anode. Ultimately, our output is equal to 3.3 volts when input is at its positive peak. Oh, zero point 0.7, no, it's sorry. 0.7 is mentioned, it's not short circuit, 0.7. If that is the case, it is plus 4 volts. Sorry. Next, during negative cycles, when input is at its negative peak, minus 10. Minus 10 means I can write minus plus like this. It is forward biased, opposite action. It is Zener breakdown. So it maintains 0.7 volts from anode to cathode. It maintains 3.3 from cathode to anode. Ultimately, it is minus 4 volts. Is it not so? Breakpoints and all we will see later, not an issue. Just I'm directly doing this problem without much discussion. Okay. So 4 volts in both positive and negative cycles. Option D is correct. It cannot have two different peak amplitudes for negative and positive cycles. Same peak amplitude. Magnitude wise, peak amplitude value of output is same. Okay. What about its breakpoints? Are they minus 4 and plus 4? No, not at all. Because there is a resistor. Okay, if the resistor is not present, the breakpoints do not change. As some resistor, the breakpoints change. And what is that? If both the diodes, anyway, our problem is done out of curiosity. I'm doing a bit additional thing. Like if both D1 and D2 are off, then what is output? Input by 2. Is it not so? So, in one case, we are getting output is equal to minus 4. If you start from negative peak to breakpoint 1, output is minus 4. And breakpoint 1 to breakpoint 2, both the diodes are off and output is equal to input by 2. And input is greater than breakpoint 2, that is maybe, right, okay, above breakpoint 2 or up to the peak amplitude. D1 is under breakdown and D2 is forward biased and output is 4 volts. So what about the breakpoints 1 and 2? Minus 8 and plus 8, not minus 4 and plus 4. Okay, so just at breakpoint 1, output is equal to minus 4. Also, it is equal to input by 2. Implies input is minus 8 volts, which is our breakpoint 1. Again, at breakpoint 2, output is equal to input by 2, also equal to 4 volts. Input is plus 8 volts, which is equal to breakpoint 2. That's it. Here the slope will change. In the previous problems, when both the diodes are off, output is equal to input, but here output is equal to input by 2, which changes the breakpoints. That's it. Okay. It's a very simple one, right? I wrote the answers directly. No need to discuss too much on this. That's it.